a tutorial on how to simulate a flow over a cylinder. This figure here shows you the problem that we'll be doing in Fluent. So we have the cylinder at the center, and we have the computational domain. We're going to have to create a geometry and also mesh it. And we're going to use a combination of structure mesh away from the cylinder, and then in the vicinity of the cylinder and in the wake, we'll be using a unstructured mesh made up of triangles. And also we're going to have a mesh near the surface of the cylinder that follows the shape of the cylinder. And we're going to do two simulations, one at Reynolds number 40, where the flow is steady, and another simulation using the same grid, a Reynolds number of 100. So we'll do that by opening Workbench. Okay, so we'll create a new case. We'll call that cylinder Reynolds number 40. So we'll start by creating the geometry first. So you open the design modeler. So we click here on the Z-axis to align it to the XY plane. You go to sketching, settings, grid, showing 2D and snap, and then draw. We'll make a circle that represents the cylinder. So we go at the origin, create a circle, and then we'll do a rectangle for the domain. Okay. We need to give it some dimensions. So the diameter of the circle, that will be 1 meter. And then horizontal, it's another dimension here. And also from the inlet to the center, it's another dimension. And then vertical dimensions, we go from here to the center. And again from the center. It's another dimension. So horizontal one would be 20 meters. Okay. And the inlet would be 5 meters from the cylinder. And the rest of them will be 5 meters to the top, 5 meters to the bottom. Okay, so we go to modeling, select the sketch we've made, concept, surfaces from sketch. This should be highlighted in yellow, then you click apply, and then generate. So this creates the basic geometry of the cylinder and the domain. Now in our case, we'll do, as you can see, we have to split up this face into other regions where we're going to specify the grid in a different way. So in order to do that, let's go back to the sketching and create a horizontal line going from, let's say, here to here, and another one from here to here, and here to here. Okay, so let's put some dimensions again. So from this point to the center, and then from this point the center. So those should be 2 meters and 2 meters. And likewise for the horizontal one, from here to here, that's 2 meters too. Here, and 2 meters also for. So basically it's a rectangular area that is 4 meters by 4 meters centered around the cylinder, and then we split into an area at the front and an area in the back. So what we have to do for this to work, we go to concept, and we go to tools, and we select face split. So it asks us to select which face we want to split. So we click, we only have one face, which is this big face. So we click on that to enable it and click apply. And then tool geometry, we're gonna split this using point and edges. So we go to this edge tool, and we select this edge and click apply, and then you click generate. So now if we go to the face tool, we should have one face which is at the top, and we have another face which is at the bottom. So now let's repeat this same step so we can split the rest of the face. We go to face split. This face is selected. We click apply. And then we have to select the line. Make sure you do line. We click apply. And then you have to click generate. So going to the face tool, we have 1, 2, and 3. So we need to split this again. So we go to tools, face split. This is selected. So click apply. And then it's split using the edge. Generate. So now we have 3 faces. It's 3 face splits actually. We have this one, this, and this. And we have to repeat this one more time. Face split. Click apply. Let's use the edge tool. Generate. So now we should have 1, 2, 3, 4, 5 faces. So what we'll do is we'll go on the edge tool. We'll select the top edge and give it a name. We call this symmetry top. Generate. We select the bottom edge. Name selection. Pick up, give it a name. Symmetry bottom. Okay, generate. Oh, this one was actually wrong. So let's delete this. We have symmetry bottom. So likewise, name selection. This is symmetry top. Okay. At the bottom, we have the top. So we have to do that for the inlet. So we go to select all these 3 edges. And then name selection, we click inlet, apply, generate. We do this for the back. Use control to select all three edges. Name selection, template. Okay, generate. And finally, we have to select the cylinder. Okay, so let's save this. Let's go. Let's name this flow cylinder. Okay, we can close this now. And we go to mesh. Okay. So under mesh, we'll do a right click, insert sizing. We go to the edge tool. We click on the cylinder. And then under element type, under element, we change that to number of divisions. We put 100 points around the cylinder. Next, we're gonna go insert inflation. So we click on the face first. Sorry, we have to click on the face. This face. And then we click on the edge tool and select the cylinder. Click apply. Then we put maximum layers of 15, growth rate of 1.1. Then we insert sizing for the rest of the edges, which is basically all the other edges. Okay. We go that to, we keep this as element size and we put element size of 0.125. And we change the behavior from soft to hard. This is to enforce these changes. We probably want to do the same thing for the cylinder. We change this from soft to hard. Okay. Then we'll do face. Oh, sorry, we'll do sizing again. But instead of selecting the edges, we'll select the faces, which is this face and this face. Click apply. The element size would be 0.08 in this case. Behavior hard. Okay. And we put insert method. So we select the entire geometry. And the method is triangles. And last, we'll do insert face meshing. We'll select the faces at the front and top and bottom. We click OK. Quadrilaterals. So if we do an update, hopefully we'll generate the grid that we wanted to do initially. So as you can see, this is the grid that we wanted to create. So we have structure grid around the cylinder, and structure grid with triangles in the wake, where we have controlled the size of the triangles. And near the cylinder, we have this inflation function, which basically propagates the grid following the shape of the geometry of the cylinder. So we want to save this. And remember the name selections. If you click on each one, so this would be the bottom. We want to verify this would be the top. The inlet, we have all three edges, outlet again, and cylinder. So we can close this. Go back, and then open setup. So I'm going to click on double precision. Okay, so we go to materials. So we'll name this fluid 40, which will have a density of 40, viscosity 1. Change create, want to override it. Okay. Then for the boundary conditions, we want to double check. So cylinder is a wall, inlet is a velocity inlet, so we click on that. We specify an inlet velocity of 1 meter per second. The outlet is a pressure outlet, and symmetry should be, we see as a symmetry, so that's correct. And in the general setup, as you can see, we have steady flow for the moment and planar, so that's also correct. So then we go to solution methods. You can use the existing, the default one. And then under monitors, we want to go to residuals. We want to increase this to 1e to the minus 6 for continuity, x velocity, and y velocity. Okay. We can also report, let's see, we can create a plot of the drag. We can always like drag plot. Okay. And we do a force report. We call this drag. We can report as a drag force instead of the coefficient. So we select cylinder and click OK. And we can also print the force to the console. So we click OK. Initialization, we want to initialize, we can put the velocity to be 1 meter per second everywhere. We click on initialize. And calculation, let's see. So let's do a maximum of 2,000 iterations. And click on calculate. So here we see how the drag force is changing with number of iterations. You can also see how the residuals are changing. And we can see the value of the residuals for the continuity on this column, the x velocity, the y velocity, and here we have how the values of the drag force. So we're waiting for the residuals to drop below the value of 1e to the minus 6. So we're still not there. The x and y velocity are on the order of e to the minus 5, but the continuity takes longer to converge. So we'll have to wait. Seems that the x velocity and the y velocity, the residuals have dropped, are about to drop below the convergence criterion. However, the simulation keeps iterating because the continuity residuals are still very high. So you can see now the x and y velocity, the residuals are below 1 e to the minus 6, and the continuity is 7 e to the minus 6, so we are slowly getting there. Actually, the calculation is complete. The residuals is actually above 1 e to the minus 6, so we can do another 2 iterations, I believe. And okay. So we continue a little longer. The residuals for the continuity will also drop. So solution is converged. So we see all residuals are below 1 e to the minus 6. And this is the drag force on the cylinder is 35.7 newtons. You could also you can calculate it as well. Let's see. Let's close this window. And we can go to post-processing to look at the results. So we can do contours, do velocity, for example. Contours. Okay, so this is how the velocity contours, the streamwise velocity contours look like. Let's see, what else can we do? We can do streamlines as well. So streamline, we can select this. And we have the streamline starts from the inlet. We have 25 points. So this is how it looks like. We could as well insert the location, the line in front of the cylinder, line that let's call this X 9.5, or line 1. X location was minus 0.5, 0.5, and 0.5 to 0.5. Put 20 or 50 points on that line. Click apply. So now we go to the streamline. And instead of starting from the inlet, we choose line 1. Click apply. Puts more streamlines. So you can see that the flow is coming from in front and it separates around this location. Okay, so that concludes the tutorial for the flow over the cylinder at Reynolds number of 140. Do a chart. Okay, so let's close this. So what we'll do now is we'll do a simulation of the flow around the cylinder in Reynolds number of 100, which is unsteady. So what we'll do is we'll do a right click where it says Fluent flow and we'll do a duplicate. So we don't need to create the geometry or the mesh, we use the same mesh. And cylinder, Reynolds number 1. Yeah, we do 100. And then so we go to setup. So the first thing we want to do in the general window, we want to change the simulation from steady to transient. So it's known that the flow around a cylinder at Reynolds number of 100 is unsteady. So we chose transient. And there's we have to change the fluid material to have a density of 100, and we'll name this fluid 100. This way we're going to be simulating the flow at Reynolds number of 100. Change, yes. So the boundary conditions are still the same. There is no change here. So what we'll do is we go to initialization. We'll initialize this. And then under calculation activities, for autosave, okay, where it says autosave, we want to save every time step. And go to run calculation. So the time step, we put a time step of 0.2 for the moment. Number of time steps, we can do 100. Maximum iterations per time step, we put 200. And then we click on calculate. So this is a history of the drag coefficient, how it changes with iterations. This is the same thing the residuals as well. Residuals have converged in less than 200 iterations, and then it advances in time. So it calculates the solution at the next time step. It tries to converge at the next time step. The solution has converged. So now we can advance 0.2 seconds in time to compute how the flow field looks at the next time step. So this is the procedure for transient simulations. So we have so far done 1, 2, 3, doing the fourth time step. So we would be time points here. It has converged, so it advances to time of 1 second. This is how the solution looks at 1 second. So this is the idea. So I'm going to let it iterate, do about 20 time steps, and then I'm going to look at the so this is the 8th time step. This is the 9th. This is the 10th. You will notice that during the first time step, it took more iterations for the solution to converge. But as you start developing a physical solution, then it's very easy to converge it. It takes less number of iterations because you have something that is already converged, and the next solution doesn't change a lot, like the flow field at the next time doesn't change a lot compared to the previous time step. So it takes very few iterations to converge it. It takes about 50 iterations now to convert the solution from one time step to the next time step. We see also how the drag force. This is a history of the drag force. Printed in the last column here. So it has done about 21 time steps. And then 4 time steps. Okay, so let's look at the solution during those 30 time steps. So I'm going to stop it at the end of the time step. I click here. So once the solution converges, calculation complete. So let's close this. So it has done 31 time steps. And let's look at the results. Okay, so this is the streamlines. Now there is something here called time step selector. So this is how the streamlines look at time step 32 or at the time of 6.2 seconds. So in the beginning, if we click this time step, this is how the streamlines look like in the very beginning. And you can see as you advance in time, the flow is developing. So we can do an animation of this and do a time step animation. So okay, we can also look at the velocity contours. So remember at the initial, when we initialize the solution, everything is at 1 meters per second. But if we do an animation, we'll see how the flow changes. Let's zoom out a little bit. Okay, and that concludes the tutorial. Save this.